Okay, so yesterday we finished off talking about the formation of imines, and we said if you use a primary amine, that amine can first attack into the carbonyl, but the carbonyl is usually protonated, so it's done under acidic conditions. And then you have this set of proton transfers where you lose the proton from your nitrogen and you add it onto your alcohol. And then the lone pair clamps down, you form a nitrogen-carbon double bond, and then you deprotonate that nitrogen. Very common mechanism, but let's take a look at what happens when we switch amine sources. Oops. So let's imagine using a secondary amine. With secondary amines, we have a little bit different chemistry occurring. So let's take this generic aldehyde. What's this aldehyde called? Oh man. You could call it ethanal, or what's the more common name? It's acetaldehyde, right? So we've got that acetate group on there. Either one of these would be acceptable. This is really similar to formation of imines, so we've got to use an acid catalyst. But in this case, we're going to use a secondary amine. So we've got two R groups coming off of the amine. When you do this, you actually get CH2 over here. And you get N, R, R. And I'll add in all of our lone pairs here. So if you notice, we're not forming a carbon-nitrogen double bond, we're forming a carbon-carbon double bond, so it's kind of like an alkene. So we call it an enamine. It's an alkene with an amine coming off of it. Let's try to figure out what's going on with the mechanism. We know that the first step, like we saw before, involves protonation of our carbonyl. It's pretty standard, so let's just go ahead and do that. And just like with our imines, we have an amine that can attack into this carbonyl, kick up electrons onto the oxygen. Got an OH group here, got an NH and two R's, so that now this nitrogen is positive. Just like we saw in the previous reaction, we've got to lose a proton from the nitrogen. To make this a neutral amine. And then we've got this OH group over here, so I'll do minus H plus. And then in the next step, we're just going to protonate our alcohol. So I'll do plus H plus. And this alcohol will grab this proton. And there we go. Looks super similar. Next step, we're going to shove off that water. Actually, I'm going to draw this a little bit differently. And there we go. It looks like an imine right now. However, it's not very stable because that nitrogen's got a positive charge on there. In our normal imine, we could just deprotonate it and neutralize it. But in this case, we've got two alkyl groups coming off of that nitrogen. We can't remove an alkyl group. So what do you think could happen? Pretty similar to our pod.
Water can come along still.
Yeah, water can act as a weak base, like we saw in our pod. And in this case, it's going to grab one of these protons on our alpha carbon, clamp down, and kick up electrons all the way up to that nitrogen so that it doesn't have a formal positive charge anymore. Now this nitrogen's neutral, and we've regenerated our acid catalyst. So this would be considered our enamine. What happens if we want to pop off the enamine and go back to our aldehyde? What could we do to remove it? Just a bunch of water, right? So we saw yesterday that Le Chatelier's principle can be used to push this reaction in the reverse direction. The mechanism is very, very similar whether or not you're going forward or backwards. It's all the same steps. All right, so you guys want to do a practice one with this? All right, let's do a practice one. Let's do this ketone. Now I want you guys to help me name it. What's this called? You could call it ethyl ketone, but it might sound like you're stuttering. What's the more appropriate IUPAC name? Yeah, 3-pentanone. So we've got 3-pentanone, and in this reaction, we're going to treat it with catalytic acid, and I'm going to treat it with diethylamine. So let's try to figure out what the product would look like if we treated this with diethylamine. Yep.
We're attaching our R groups to our secondary amines. Do they have to be the same R group, or can they be different?
That's a good question. Usually they're the same R group, but they can be different. If your R groups are different, then you have to start worrying about regiochemistry. So which side is which R group on? At least with the imine. For enamines, it doesn't matter that much. Yeah. Do you guys want me to walk through the mechanism, or do you guys want a little bit more time to work on it? More time? Okay. All right, it looks like most people are getting pretty close. So let's walk through this a little bit, at least the early steps. We know we're going to protonate this carbonyl. So we've got the oxygen with the formal positive charge. Now we're going to take our diethylamine. This diethylamine we know can act as a nucleophile, add into the ketone. We've got two ethyl groups coming off of this nitrogen as well as a proton, so this nitrogen's got a positive charge. Now what? Proton transfer. So let's do minus H plus to show removal of the proton coming off of that nitrogen. Oops, sorry, that should be neutral. We've got a lone pair there, and then we've got OH over here. The next step we saw with our imine and enamine formation is protonation of the alcohol, so I'll do H plus.
Is it okay if first protonate the alcohol, then deprotonate the nitrogen, or do we not want two positive charges?
Yeah, that's a good question. In general, you want to keep your charges to a minimum. So try to deprotonate your nitrogen and then protonate your alcohol, because it's very unlikely that you'll have a doubly cationic species. So we'll have this nitrogen with the lone pair. Now we've got water with an extra alcohol with an extra proton, which is a good leaving group. We'll kick off this water. This nitrogen has a positive charge. We're not quite done. Now what? Yeah, we're just going to grab one of these protons. Does it matter which side we grab it from? No, but like, was it Van asking before? Or somebody in the back was asking what happens if we've got different R groups. Then we do have to worry about mixtures of products, so we may have a double bond on one or the other side. So in this case, water will come, clamp down, kick up electrons. I'll actually draw out our ethyl groups just because I think this molecule looks cool. And there we go. So we were able to form our enamine from this. There are a couple of other nitrogen nucleophiles that we do have to consider. So I really quickly wanted to present two other ones.
Yeah, no.
Yep.
So you know how you picked up the bond on the right? Can we do it on the left bond of the nitrogen?
Yeah, because this is a symmetric molecule, it will only result in one product. If it were unsymmetric, then we would get two products out.
We might have already covered this, but would you get a different chemistry? Never mind.
Yeah, so let's say if our starting ketone wasn't symmetric, that would mean we could get two different products out of this reaction. But because it was a symmetric ketone, we only get one product out. So if the double bond were on the right side, it would still be the same product.
I mean, like Z or E.
Oh, for this alkene, do you guys think it would be a Z or an E alkene? What do you guys think? Oh man, we're forgetting our alkene stuff. Let's go back and review. So remember, we can draw our invisible line down this alkene, and then we have to look at it. What's higher priority, this methyl group or the hydrogen? The methyl group. So this would be priority 1. And then on this side, what's going to be higher priority, the nitrogen or the carbon coming off? Nitrogen. So this would be 1. So this would be Z for Z same side. So this would be a Z alkene that we're forming.
But I think the question was more why Z as opposed to...
Oh, in this case, you could get both out of it. That's a good question. Yeah. All right, let's take a look at the other nitrogen nucleophiles. Let me actually write this down too so we know. So you'll get a mixture of E and Z out of this. Good catch. So let's do other nitrogen nucleophiles. The first one I want to look at is with a generic ketone. You can treat this with catalytic acid. And this guy, now the question is, will the nitrogen be more nucleophilic or will the alcohol side be more nucleophilic? What do you guys think? What's typically more nucleophilic? The right side of a row or the left side of a row? In this case, the nitrogen will actually be more nucleophilic than the oxygen. So if we look at this, the nitrogen will add in first, and will we get an imine or an enamine? Will the double bond be between the carbon and the nitrogen, or between a carbon and carbon? Carbon-nitrogen. This is a primary amine. So if we do this, we get a nitrogen with an OH coming off. And this is a special intermediate. This is called an oxamine. And the byproduct of this, like we saw before, is going to be H2O. So oxamines are pretty common. Another nitrogen nucleophile that we saw in our pod is where you can take a ketone, treat it with catalytic acid and hydrazine. And when we do this, we still get an imine. However, this is called a hydrazone. And the byproduct of each of these reactions is water. Hydrazones are really useful intermediates in organic chemistry, and I'll show you guys why here in a second. But nitrogen's an excellent nucleophile. It will attack in, kick off water, and then we can start doing chemistry on these unique functional groups. And the reaction we're going to talk about next is called the Wolff-Kishner reaction. Is it okay if I change pages?
No.
Right, 1 second. All right, the Wolff-Kishner reaction involves formation of a hydrazone. So I'm going to choose the generic ketone. So I'll do, H plus. And hydrazine, and if we do this, we know we're going to form our hydrazone intermediate. Along with water. Once you form this hydrazone, a cool trick is you treat this with, this should be a one-way arrow actually. You treat this with potassium or sodium hydroxide, water, and heat. And you end up forming an alkane. So you completely eliminate the substituent coming off of where the ketone used to be. And we form N2 gas. In this case, why didn't I show this as an equilibrium arrow? Yeah, because anytime you bubble off gas, it's going to drive the equilibrium to completion. Even if the reaction's super slow, forming a gas is very thermodynamically favorable, and you push the reaction all the way to the right-hand side. So now let's take a look at the mechanism for the Wolff-Kishner reaction. Oop. We know the first step for all of these reactions is protonation. So let's do that first. Shoot. Sorry. I don't know if my battery's dying or what's going on. There we go. So we've got our aldehyde, or sorry, our ketone. This also can work with an aldehyde, but normally it's done with ketones because it's very easy to reduce aldehydes and then go from there. We'll protonate our ketone. Then in the next step, we'll have our hydrazine attack into our ketone, so the ketone will become an alcohol. And then I'm going to kind of expedite things by just indicating a proton transfer, kind of like we did with our pod. So I'm going to move the proton from this protonated nitrogen right here over to the alcohol. And then we know this nitrogen lone pair that is formed will clamp down, kick off our alcohol. And we're at our protonated imine right now. So let's do our last proton transfer, and then we'll get into the next step of our Wolff-Kishner reaction. So in this step, we'll show our final hydrazone. Whoops. I'm actually going to draw out both of these nitrogens with their lone pairs. Okay, so we've got this very important intermediate. We know in the Wolff-Kishner reaction, the next step involves base. So if we've got a strong base around, it's not super favorable, but some of this base can actually come, grab this proton, which will clamp down here, and then push electrons onto this nitrogen. Or onto the carbon, excuse me.
That can't happen with just H2O.
No, you typically need a stronger base to drive this. So now we've got the nitrogen-nitrogen double bond. But this carbon's now got a negative charge on it. We formed water during this reaction. So this carbon will quickly grab a proton back from the water. We're almost there, but we've reformed our hydroxide. What do you think this hydroxide will do next? Yeah, similar reaction. It'll go after the proton coming off of that terminal nitrogen. This will clamp down. And we're forming a nitrogen-nitrogen triple bond, right? So we're generating nitrogen gas, and we're going to kick electrons down to this carbon. This is where that one-way arrow is so important. We saw the previous step really isn't that favorable. However, by liberating nitrogen gas, even though we're not forming much of it, we're driving the reaction to completion. So now we've got deprotonated cyclohexane. We've got N2, all right, gas. And then we've also got water. We know that alkanes aren't very happy with the negative charge, so this alkane will quickly come, grab this proton, and we'll regenerate our base. So it's a pretty nice way of going from a ketone or aldehyde directly back to your alkane. We saw another reaction that was really similar to this. Does anybody remember the name of that reaction? I'll give you guys a hint. If we want to go from here, oops, to here, what reagents did we need? What was it? Yeah, the Clemenson reduction. And what reagents did we need for that? Yeah, zinc, mercury amalgam, and then HCl. So you can imagine a lot of chemists aren't super fond of working with mercury. The Wolff-Kitchner reduction is a really nice workaround that's much greener and avoids the use of heavy metals. So you can use either of these for the system I've got shown here. However, the Wolff-Kitchner reduction will work on a variety of different systems beyond just Clemenson reduction. Clemenson reduction is typically only done with ketones that are right next to a benzene ring or an aromatic molecule. Yep. Yeah. Yep.
So for this mechanism, if we didn't have the base, we would just stop at the...
You would stop at your hydrazone. So if you don't have base, you're not going to continue on. Those next steps have to be pushed a little bit.
And where do we get the base from?
So in this reaction, you'll typically form your hydrazone, and then you'll throw base into your reaction mixture to help drive the reduction reaction.
So if it's on the problem, it would say that we have a base.
Yeah, I would indicate that there's a base. Yep.
In the textbook, like, as a hydrogen source, it said it was like a nitrogen-containing molecule. Do you want us to specify a hydrogen source for these reactions?
A hydrogen source?
You know, there's like H plus and H minus, and like what's your driving reaction for that?
Oh, are you talking about for proton transfers, what's doing it? Yeah, that gets pretty complicated. If you look in your book, they'll use one set of reagents. If you go into a different textbook, they use a different one. The reality is with acid-base equilibria, there's a lot going on. So I don't want you guys to get too bogged down in remembering what's doing the proton transfer. I do want you to remember that there is a proton transfer, though. In this case, it's usually going to be excess hydrazine facilitating the proton transfer. So it will act as a base and the acid. So it can do both. Yep.
Plus minus H plus. You're saying the alcohol is taking the hydrogen, the proton from the hydrogen?
Yeah, so in this step right here, basically I'm just saying this proton is getting moved over to that oxygen.
Is the alcohol actually taking it, or is it just through a series of protons?
No, it's through a series of proton transfers. I just didn't want to have to fill up an entire page showing proton transfers.
Okay.
All right, let's do a little bit of practice with this because sometimes it can be tough to see what's going on behind the reaction. So I'll give you guys some hypothetical quiz problems. 4 points. Fill in the box. We've got acid catalyst. I'm going to say we're going to drive off water during the reaction. And I also want you to provide the other reagent for an additional 4 points. This is a big problem. Don't mess it up.
You're giving us the answer.
Yeah, but I'm not giving you the reagents. So the question is, what reagents do you need in order to make this product?
Can I ask a question?
You can ask a question.
Would that nitrogen with the ring, could you consider the ring 2 R groups?
Sure.
Okay.
Nope. Once you guys think you've got it, you can drop your pencil loudly so I know. Oh, shoot. I apologize. I've goofed up here. The double bond should be right there. That would have been impossible using the chemistry we just did. Sorry. This should make it significantly easier. All right, I'll show you guys a few tricks when you're looking at these reactions. First thing to ask is whether or not you're making an imine or an enamine. Have we made an imine or an enamine here? Enamine. We know with enamines that we are typically using, or we always are going to be using, a secondary amine. So let's make a couple notes. We've got an enamine. We know that in here this must be a secondary amine. And then we know that when we form an enamine, that this used to be a CO bond, right? So if we break this apart, we can say that, well, in this case, this probably was our amine, and then this side over here used to be our ketone, right? So if we fill in these boxes, we know that our ketone was likely cyclohexanone. And then if we look at our amine, it's okay to use a cyclic amine. So in this case, our amine is secondary. It will react with cyclohexanone and will form our desired product. All right, let's try another one. And this time I'll try not to mess up the structure. We've got acid. I'm going to drive off water during this reaction to favor formation of our product. And this is going to be our desired product. So what we need to do is to figure out what reagent or reagents we need in this box right here. And make this box bigger.
That's a notebook coming off.
Yep.
Okay, gotcha.
How many of you guys think you got it so far? A few people? So first question, are we making an imine or an enamine? Enamine, right? We've got an alkene. So now the question is, where do you think the CO double bond used to be? Yeah, it must have been right here, right? So we're making a new nitrogen carbon bond in this position. So if we think about it, we know that there used to be a CO double bond where this red carbon used to be, right? We formed that double bond right here during the reaction. Now we've got to fill in the rest of the stuff coming off. We know we've got a methyl group coming off down here. Then over here, we've got 1, 2, 3, 4. And then on this fourth position, we've got a nitrogen. This nitrogen has a methyl group coming off. And then it's also got a hydrogen right there. So if we think about this, this is an example of an intramolecular enamine reaction. Does that make sense? So just try to identify the position that you think the bond was formed in and then deconstruct it from there. Are there any other questions with formation of enamines? All right, I think we're going to cut off a little bit early, at least regarding lecture, but I did want to give you a quick hint on the pod. So today's pod, or I guess due on Monday, looks a little bit different, but I'll give you a hint. It's very similar to the reactions we've seen, just in reverse. So look at the reactions you've done and try to see if you can do them both backwards and forwards. It's very, very similar. All right, enjoy the sunshine.